In the last lecture, we looked at divide and conquer as an algorithm design strategy and recursion to implement divide and conquer algorithms. In this lecture, we will continue solving some problems using recursion. The first problem we will be looking at is printing a triangle recursively. Here is a 7 by 7 triangle, lower matrix triangle, where you print 1 star on the first row, 2 stars on the second row, and 7 stars on the last row. Obviously, you can write a nested loop to solve this problem, but our goal in this lecture is to design a recursive algorithm that achieves the same thing. So the base case for this problem is print nothing if n is less than or equal to 0, meaning that if the size of the triangle is less than or equal to 0, there's nothing to print on the screen. Otherwise, here is the recursive formulation. Look at the red triangle on this pattern. That is a triangle of size n minus 1, meaning that it has n minus 1 rows and n minus 1 columns. So if we can recursively print a triangle of size n minus 1, to print a triangle of size n, we just need to print this last row after the recursion returns, right? So that's the recursive formulation. The base case is print nothing if n is less than or equal to 0. The recursive formulation is you have a problem of size n, that is, we would like to print a triangle of size n by n. We can first print a triangle with n minus 1 rows and n minus 1 columns. That's the recursive formulation. Then after we return from the recursion, we can print the last row with n star characters. And here's the actual code for it. So here is our triangle function that takes a problem of size n, meaning that it's going to print a triangle of size n by n. The base case is if n is less than or equal to 0, return, do nothing. Otherwise, recursively print a triangle of size n minus 1. When we return from the recursion, now a triangle of size n minus 1 has already been printed on the screen. I just need to print the last row. The last row is, I can write a for loop that iterates from 1 to n and prints n star characters on the screen. Of course, after printing the row, I need to put a new line character to take the cursor to the beginning of the next row. Let's now run this recursive function to print a 5 by 5 triangle. The initial call is triangle 5. The problem size is 5. It's not the base case. The first thing that we do is call triangle, but reduce the problem size by 4. So let's first print a triangle of size 4. That's still not the base case. So we are going to make another recursive call, but this time the triangle, the size of the triangle is 3. Then it's going to be 2. Then it's going to be 1. And it's going to be 0. So 0 is our base case, remember. So basically, we started with a problem size of 5. By reducing the problem size by 1, we eventually reach the base case, which is when n is equal to 0. When n is equal to 0, we are at the base case. So this statement is, we hit this statement, n is less than or equal to 0, and we return. So printing nothing. So we print nothing at this point. But after we return to the context of triangle 1, we are right in here in the next statement, and we are supposed to print 1 star characters and then a new line character because n is equal to 1 in here. So this is going to print 1 star character and then take the cursor to the beginning of the next line. When we return from triangle 1, we return to the context of triangle 2. We are here, n is equal to 2, so we are supposed to print 2 star characters and a new line. So that takes us to the beginning of the new line. Now we return to the context of triangle 3. That's going to print 3 star characters and a new line. Then when we return to the context of triangle 4, that's going to print 4 star characters and a new line. And eventually we return to the context of triangle 5, that's going to print 5 star characters and a new line. And then we return to the main function, which is supposed to call the initial triangle function. Of course, this is wrong. It should have been 5. In this example, I am printing a triangle of size 5. This is example 3 actually. So this is example 3 where I am making a call to triangle, passing 7 as the argument. This is the same code. I'm just going to execute it so that we can print a 7 by 7 triangle on the screen. And here's the terminal. As you can see, this is a 7 by 7 triangle on the screen. It's a lower matrix triangle. Let's now move on to our second problem of today. Finding the first digit of an integer. You are given a positive integer n. Write a recursive function to return the first digit of the number. So if the parameter to the first digit is 34257, the first digit, meaning the most significant digit of this number, is 3, so it should return me 3. If I just pass a one-digit number like 8, then the first digit and the only digit in this number is 8, so it should return me 8. So the first the way you approach these kinds of problems is first you identify the base case. So we say if n is less than or equal to 9, meaning that if the number only has one digit, and that's our answer, so return n. Otherwise, take a number that has more than one digit, like 34,257. The way we can approach this problem is as follows. We need to reduce the size of this problem. And we can do that by just peeling off the least significant digit, meaning 7, from this number. And to peel off one number from one digit from this number, we need to divide it by 10. So recursive formulation is peel off the last digit of n and recursively find the first digit of the remaining number. So that means we need to peel off the least significant digit by dividing the number by 10. So that gets rid of the 7 in this example. And now you're left with 3425, and now we are recursively supposed to find the first digit. So let's run it through an example. Let's say the number is 654, and we are trying to find the first digit. So recursion is going to start with 654. It's not the base case. We're going to peel off the last digit, so we are going to be left with 65. So recursively find the first digit of 65. This is still not the base case. We peel off the last digit. We are left with 6. 6 is less than or equal to 9, so we hit the base case and we return 6. So here is the code for it. So integer first digit, integer n. If n is less than or equal to 9, return n. That's our base case. Otherwise, the recursive call is just peel off the last digit by dividing the number by 10, and then return the result. That's it. We don't have to do anything after we return from the recursion. The result of the recursive, the subproblem, is also the solution to our bigger problem. So let's run this code with a number 3456385. Again, we enter the recursive function. It is not the base case, so we peel off the last digit. So we are left with 45638. Again, this is not the base case, so we peel off the last digit. You're left with 3563. Peel off the last digit. You're left with 456. Peel off the last digit. You're left with 45. Peel off the last digit. You're left with 4. So when we enter this call, first digit with 4, we hit the base case, because if n is less than or equal to 9 and n is equal to 4 in this case, just return n. So we return 4. When we return to the context of 45, as you can see, we don't do anything. We just return the result. So the solution to a problem problem where the number is equal to 4 is also the solution to this problem where number is equal to 45. The first digit is the same for all of these numbers. So we just return 4. We return 4, 4, 4, 4, and eventually we return 4. So bottom line is, when the solution to the subproblem in this example, in this problem, is also the solution to the original given problem. So we don't have to do anything after returning from the recursion. And this is example 4. So let me go there. This is example 4. Let me just execute this so that you see that the first number is returned correctly. Obviously, you can always write a iterative function to find the first digit. And I advise you to actually implement this recursive function iteratively so that your programming skills improve. Let's now change the problem a little bit and define a new problem where we are going to count the number of digits of an integer. The problem is you are given a positive integer num. Write a recursive function to count the number of digits in num. In the previous problem, we were trying to figure out the first digit of the number. Here we are trying to count the number of digits. So the number of digits on 34257 is 5. It has 5 digits. And for 8, it only has 1 digit. So if the input to num digits is 8, you need to return 1. If the input is 34,257, then you need to return 5. Again, the base case is very simple. If the number is less than or equal to 9, meaning that it only has one digit, return 1. That's our base case. We don't have to divide the problem any further. Otherwise, we use the same methodology. Basically, peel off the last digit and reduce the problem size, reduce the number of digits that this number has. So peel off the last digit. In this case, it is 7. So you're left with 3425. Recursively count the number of digits in 3425. And now when we return from the recursion, we have to add 1 to it because the last digit we peeled off is one of the digits of this number. So that's the recursive formulation. And here is the code for it. So if the number n is less than or equal to 9, return 1, because a number that only has one digit, we have to return 1. Otherwise, peel off the last number by dividing the number by 10 and recursively compute the number of digits in the smaller problem. When we return, we have to add 1 because we just peeled off one digit, so that's the one that we need to add to the result. So let's run it for this number, 4, 5, 6, 3, 8, and 5. When we enter recursive to this recursive function, it is not the base case, so we are going to peel off the last digit, and we are going to be left with 4, 5, 6, 3, 8. Peel off the last digit, 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 and we are now at the base of our recursion 3, meaning that now the number is 4 now, which is the base case, so this is going to return me 1. And when I return from the recursion, I'm going to return to this step, and 1 plus 1. I need to add 1 to it because 5 is the other digit of 45. So it's going to be 2. When I return to the context of num digits 4, 56, I need to add 1 to it. So it's 3. Then 3 plus 1, 4. 4 plus 1, 5. And 5 plus 1, 6. So as you can see, this number has 6 digits in it. Again, you can easily write a iterative function to count the number of digits in a given integer, but this is the way to recursively run it. And this is example 5, so let's go there. So let me go to example 5 and run this code. Again, this is my number. I'm just going to run the code just to show you that it works correctly. And as you can see, this number has 6 digits. Let's look at our next problem, counting the number of even digits of a given integer. You are given a positive integer num. Write a recursive function to count the number of even digits in num. So here are some examples, num even digits. If the input is 3, 4, 2, 5, 7, obviously there are two even numbers, even digits in it, so it's 4 and 2. So the count is 2. Number of even digits 8 is 1 because there's only one digit and that's even. Number of even digits 153, it should return 0 because all the digits of the number are odd numbers. So how do we approach this? Again, let's look at the base case. The base case is when we have only one digit. If n is less than or equal to 9, then in that case we need to return 1 if the digit is even. Otherwise, we need to return 0. So for example, if the digit is 8, if the number is 8, which has only one digit, we need to return 1. But if the number is 7, for example, it is a number with one digit, but the digit is an odd number, then in that case we need to return 0. So this is what this is saying. If look at the number, if it is an even number, then you return 1. Otherwise, you return 0. Recursive formulation is again the same, so just peel off the last digit, compute the number of even digits on the rest of the number. Then now we need to look at the last digit that we just peeled off. If it is an even digit, then we need to add 1 to the result of the subproblem. Otherwise, we just return the result of the subproblem. And here is the implementation of this recursive function. So it's number of even digits. It takes an integer n. If the digit is less than or equal to 9, we check the following. If this is a ternary operator, so check if the last digit, which is n modulo 2, is equal to 0. If the last digit is equal to 0, that means it is even. So I need to return 1. Otherwise, the last digit, meaning the only digit in the number, is an odd number, odd digit, so I return 0. Otherwise, I take the last digit, I say n modulo 10, and compute the result to the subproblem by peeling off the last digit of this number. So n divided by 10 is peeling off the last digit of this number. So I get the result to the subproblem. Now I am looking at the last digit that I just peeled off here. If the last digit is an even number, I am incrementing the answer by 1 because the last digit is also an even number. Otherwise, I'm not doing anything to the result of the subproblem. I'm just returning it. So let's run this for this example. So number of even digits, this is the number that's input. That's not the base case. So we're going to peel off one digit at a time. So peel, 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 peel. Eventually, we are going to be left with a number that's only one digit, that only has one digit in it. And when we come here, if n is less than or equal to 9, we are going to do this check. If n modulo 2 is equal to 0, meaning if this digit is even, then we're going to return 1, which is the case here. So 4 is an even number, so we are going to return 1 from here. So when we come back, we're going to come back here. The last digit in 45 is 5, which is an odd number. That means we are not going to execute this if statement. So the last digit is not 0, so answer is not going to be incremented. We are still going to return 1. So 45 only has one even digit in it. When we come to the context of 456, again, look at the last digit. The last digit in here is 6. 6 modulo 2 is equal to 0. So I'm going to increment the answer that's coming from the recursion the sub problem. That was 1. I'm going to increment it by 1. That's going to be 2. So I'm going to return 2. As you can see, 456 has 2 digits that are even. So 4 and 6. In here, look at the last digit, which is 3. That's an odd number, so I'm not going to increment the result that's coming from the subproblem, so I'm going to return 2. In here, the last digit is 8, so that's an even number, so I'm going to increment the result of the subproblem by 1. I'm going to return 3. As you can see, the even digits in this number are 4, 6, and 8. And when I come here, the last digit is 5, which is an odd number, so I'm not going to increment the result that's coming from the subproblem. I'm just going to return 3 to the caller, which is the caller in main. As you can see, this number has 3 even digits in it. This is example 6, so let's go to the actual example. This is example 6, and this is the number of even digits. Let me just execute this so that you see that it works correctly. There you go. So that's the number in the example, and it has 3 even digits. So let's change the number. For example, let's say the number only has 1 even digits. So let's do 1 3 5 7 9 3 3, and then let's put a 4 in there. So it only has 1 even digit. So when we run this thing, we should get 1 as the result. And there you go. It only has 1